I'm going to tell you about a project that we put out a month or two ago, a couple months ago, with David Reutter, and with the title, the paper is the same title, and you can see these slides on my website. So there we are. So the structure of the talk that I want to tell you, I'm going to tell you the main theorem and kind of how to think about it. The main theorem that I'm gonna present to you is, like, it is an improvement on what's in the literature, but the kind of meaning and use cases are already recognized in the literature. What I'm really excited about is we do have a technical improvement and also the methods that we used to do that. So I'll tell you about the main theorem, and then I'll spend some time kind of talking about some of the techniques that are currently being developed in infinity categories. And then I'll try to sort of give you a sense of how we use them for this theorem. So here's the main theorem, and here it is in full glory. So the theorem that we prove is the following: I take an infinity 3 category, and I take a retract in an infinity 3 category. So what is a retract? A retract. I've decided to pick my category to have some basic object. Maybe that's called the vacuum. Maybe this is called the 3 category of 3-dimensional phases of matter. And I pick some sort of object I think of as the vacuum, some other object, and morphisms in and out, which compose to the identity. So it's a one-sided inverse. I'll call that a retract or section retract pair. And then I want to assume some adjunctability on my retract. I want to assume that the incoming arrow is a left adjoint, that the outgoing arrow is a right adjoint, and then there's 2 conditions that are equivalent. You can look at, if you have a comparison between the identity and the composition, and you have this adjunctability, you get canonical comparison maps between adjoints of those arrows. And I want to ask those canonical comparison maps to have some adjunctability. So if you're in a very, very topological TFT mindset, then adjunctability conditions are completely given to you, and you don't have to check those conditions. And then the theorem is, then what we do is we look at a square like this, filled in with kind of in this, so I'm in some ambient 3 category, so this is a square of 2 morphisms, so this is some element in the category of 2 morphisms from the identity. Let's see, the outside of the square is the identity on the unit object and the identity on the unit object. And the statement is that that element in that category is actually, well, first of all, it's a bialgebra, and it's almost a Hopf algebra. The actual statement is that its opposite bialgebra is a Hopf algebra. And I think this is one of the things that I'll come back to that, like, really excited us in the theorem. It's a fun exercise to do the following. So most Hopf algebras you know have an antipode which has the property of being invertible. Like, that map is invertible. There are Hopf algebras that violate this. They're a little bit hard to construct. They arise, among other places, in categories so if you have a Hopf algebra whose antipode is not invertible, what that tells you is that the monoidal category of modules for that Hopf algebra, every object has a left dual, but not every object has a right dual. And that can happen. And so we build that type of situation. And I didn't write it on the slide, but our theorem is sharp. Like, every Hopf algebra we can pull out of this. So this is exactly characterizing. This is sort of a Tanakian statement that every Hopf algebra can get this way. So let me tell you what this Hopf algebra looks like. So now I'm going to sort of give you the topological picture, the pictures that you might see in the literature already. And I really want to flag already, I think some version of this has been rediscovered a number of times. I think the best papers are beautiful papers by Dan and Constantine and by Tudor and Wenjin Yu on this that recognized this and used it to do some actually sort of interesting physics. So here's the same square. I've just redrawn it in kind of Poincare dual picture, like instead of pasting diagrams, I'm drawing it in string diagrams. And then the Hopf data, the multiplication, comultiplication, are just these bordisms. You can take a square, 2 squares, and fuse them in a kind of one diagonal direction, or you can unfuse them in the other diagonal direction. And the fact that you can fuse these in those ways, that's exactly the adjunctability conditions I gave you. Like I've used up all the adjunctability that I started with to even write down these pictures. And so really, like, I want to repeat this, that both in Dan and Constantine's papers and in Tudor and Wengen's papers, the interpretation going on that they were using is they really wanted to think of the ambient outside world as some type of vacuum, and they really want to think of the interior of this square as some type of material, and they really want to think of this as a pair of transverse boundary conditions. The fact that they're transverse boundary conditions was the fact that these are not, that this corner is invertible. That's the transversality statement. And then recovering Hopf algebras, like that's a useful way to, that's some of the information of your system, is that Hopf algebra. So let me show you sort of some of the reasons, the non-coherent reasons why this is a Hopf algebra. So the fact that you can fuse, the fact that the identity, that these are a one-sided inverse, the way you can think of that is it's saying that anytime I draw a bigone, that bigone can just be cut out. It can just evaporate. And there's other conditions that are similar when you start unpacking it, that sort of bigonal holes can also be cut out. So for instance, you might check, like, here's one of the axioms of a Hopf algebra. It's the axiom that if you take the multiplication and then patch on the co-unit, that the co-unit should be should be an augmentation for that algebra. And the way you prove it, or a topological reason for this to be true, is you just massage this bordism, and then you recognize that right here is a bigone between red and blue, but bigones are the same as identity, and so I can snip that out. The most interesting Hopf axiom, the one that Hopf cared about, Hopf didn't know about antipodes, by the way. The one that Hopf cared about was the fact that if you co-multiply in two variables and then multiply, that's the same as multiplying and then co-multiplying, that these are homomorphisms for each other. And the same thing you can do, you can draw that bordism, and then if you look inside this bordism, let's see if I can draw it, there's this circle here. You can find a solid black circle in the middle of the bordism. And I probably should have drawn this. If you stretch your bordism out, you can stretch it out so that what you see is this red surface that I've drawn going way up. You can make it kind of go flat, and you can make the blue surface go flat. And then you sort of see two parallel surfaces with a hole drilled through it. And the fact that you have GF is equal to the identity means that hole can also be snipped out. And so you can cut that neck, and then you can kill that bit of genus. So that's the topological reason for this to be true. Okay, great. So I don't care about topology, I care about higher categories. And the problem with topological arguments is, one, you might or might not believe in the cobordism hypothesis. Another is that if you're actually trying to do category theory correctly for this type of stuff, you have to track a lot of framing data. Even if you do believe in cobordism hypothesis, you actually have to carefully track, as you do topological manipulations, what's happening with source and target directions. And none of these pictures was I being very careful to track that type of stuff. It's possible to do it, of course, but it takes some, it's like annoying and technical work. You have to come up with good notation for it. I think even more importantly, like, I want to apply this theorem, I might want to apply this theorem in a very infinity-categorical coherent context. So I didn't tell you the applications I have in mind. The applications I have in mind are not the ones that Dan and Mike or that Tudor and Wengen cared about. The applications I have in mind, I've sort of, well, I mentioned kind of just general Tanakian reconstruction, maybe in a coherent infinity context. But the other application I have in mind is that I know a lot of retracts in higher categories. If I have a bordism category and I have a disk embedded in a manifold, I can surgery the boundary of that disk, and then I can cancel that surgery off. And that's always a retract. And so bordism categories give me a very, very large source of retracts. And what that means is bordism categories have a lot of Hopf algebras in them. So, and I'd like to do that coherently. And tracking coherence is annoying. There are machines where you can like stick the notion of bialgebra into the machine, and then it churns for a while and writes out some list of infinity much data and properties that you'd have to check in a kind of combinatorial model. But you would never want to check infinity many bordisms and infinity many diffeomorphisms. That would be a terrible way to do algebra. The other reason why I don't want to do this type of stuff, is sort of part of this coherent stuff is, for instance, I'm going to need that this is all nice and functorial. But also another one is that in my theorem, I didn't need as full adjunctability. And I have examples where I might not have full adjunctability. And if I'm drawing manifolds, it's like dangerous to draw manifolds to compute when you don't have full adjunctability. Because you might not actually, I think, like Thibaut and Ben are working on this great project right now that's exactly harnessing contexts where they don't have full adjunctability, and therefore studying cases where they cannot cancel things off, and so that they don't have a diffeomorphism invariant. And if you draw manifolds, that's really dangerous. Like, you might think, oh, these two manifolds are diffeomorphic, and they can both be written with the data I have, therefore they must be computing the same thing, and that might not work, because the way they become the same might require more data. And sort of part of this thing is I told you, I can write down Hopf algebras using my theorem, which don't have invertible antipode. If you have all of this manifold technology, here's the antipode for you. It's just the 180-degree twist on the square. Plus, you have to think a lot about what's going on with the framing data in that 180-degree twist, because it doesn't look framed.
What does it mean, presentably braided?
Where did I, a presentably braided category is category which is locally presentable, and the monoidal structure is closed. Sorry, yeah. So actually, I lied to you. I don't actually know how to write down every Hopf algebra in every braided category from my machine, and it's possible I can. But what I know how to do is every presentably monoidal category. So every braided monoidal presentable in category with a Hopf algebra in it, then I can write that down with my machine. So up to sort of taking colimit completions, I can write these down. But the way I can do this, so the way I can get every category uses sort of tricks from presentable category theory. Anyway, the 180-degree rotation is obviously invertible. And I told you I can get things that don't have, you might not believe me, but I told you that I can reproduce things that don't have invertible antipode. And so it can't be coming from this picture. So okay, now I'm going to kind of go into some of the technical stuff that we did. So those of you who don't like technical stuff should just sort of fall asleep for 20 minutes. Okay, so I'm going to work in the world of infinity categories. By definition, an infinity n category is a category enriched in infinity n minus 1 categories. That definition by now parses very well. It took a couple, while to get these words to parse in a nice way. And then infinity categories is the limit of this notion. Every space is in particular, every group weight is an example of a category. Therefore, every category enriched in group weights is an example of a 2 category, and so on. So these things live inside of each other. And I just want to take the limit. I have to take the limit in a world where I have good presentability, good kind of ability to take colimits. If you take just the actual union of these categories, you get the ensemble of all higher categories in which each element in your category has a category number. And so that ensemble doesn't have real infinity categories, it just has arbitrarily high categories. I want to give myself actual infinity categories because I want to be able to, and an actual one can be written as some union of its subcategories of different dimensions. A good way to close off and give yourself those unions is just say the word sheaves. That's one way to do it. The people who know presentable category theory can translate, and the people who don't know can ignore that word. And the way I want you to think of a higher category, a useful way to think about higher categories that's being, I think, really kind of under active development right now, is to think that when I draw a category, let me look at the first picture I drew on the first slide. First picture I drew looks like I have some vertices and some edges and some cells filling them in. So categories look a lot like cell complexes, but they look like cell complexes in which every cell has a direction. And that's I want to say that's like a useful way to think about categories. It's not just a superficial thing. So there's a program that's ongoing right now to really kind of think about infinity categories as kind of a directed version of algebraic topology, a directed version of cell complexes. The most basic thing, well, one of the most basic things you can try to do with cell complexes, you can try to multiply cell complexes. If you have two cell complexes, you can take just their product. And if you have directed cell complexes, you can say, well, what should I want to write down a product of those cell complexes, and I need to consistently assign directions to everything. And in the category literature, this is called the gray product, or the tensor product, or the lax product. And you know actually already how to do this. So you know what the rules should be. The rules should be that if I have a cell, the boundary of a cell is interpreted in category theory as something about the source and target of that cell. And so the rule for producting, if I want to tell you a direction, I just have to tell you sort of which part's the source and which part's the target. And I'm just going to decide a rule, and the rule I'm just going to decide is I would like the standard rule for the boundary of a product. The boundary of a product, if you do a first course in algebraic topology, you might write down something like the boundary of a product is the boundary of the first one plus the boundary of the second with a sign that you pick up when following some rule. And you might have different sign conventions. I don't care. They're all equivalent. I will pick this one, but it doesn't really matter. You make a consistent choice of sign rules for how boundaries should go. And then you ask, can I make those consistent choice of sign rules on cellular chains that you've learned when you were a child, can you uplift those to actual directions on the cells? And the answer is yes. It's a slightly hard thing to do, but Tim Campion showed that the worlds of infinity categories has a consistent tensor product, which is uniquely determined by wanting this rule and also wanting to be closed monoidal, meaning there's Hom tensor adjunction in each variable. And it's really important to point out that this is not just a Cartesian product. This is more interesting than taking a product. It's not just selected by kind of the usual one-dimensional category theory that we've grown up with. And one way to see that it's not a usual product is that it's not even symmetric. That if you take the product of two cell complexes, I'll draw some pictures on the next slides. If you take the product of two cell complexes, the directions you put in, if you switch the order, you've explicitly chosen a different, you might actually have, there might be a sign, this is what you're used to all the time. That if you switch the order of two odd-dimensional cells, you have a very obvious sign problem. And a side effect of this that I don't know what to make of this yet. But a side effect of this is that it's not symmetric. It is like a star monoidal structure in the sense that if you take opposite categories, you can switch orders around. So the multiplying the other order is related to multiplying in some order. I don't know what to use that for. But every quantum mechanics person likes star algebras, and I think this is sort of a thing to pursue, but I don't have anything useful to say. So let me show you some pictures. So if I take the product of two 1 cells, I get a 2 cell, of course, a square, and it's directed in some way. The rule, of course, was always that, why can I not go back? The rule was always that I don't change the direction of the left entry in my product. I might change directions of the right entry. So here's a picture of a 1 cell. It'll be later. I'm going to start really drawing Poincare dual pictures. So I've drawn a Poincare dual picture. I have some conventions that I like, and I'm imposing on you and not telling you about which directions are different directions when I'm drawing pictures. I can tell you roughly. My directions is that when I draw pasting diagrams, my first direction goes horizontal and my second direction goes vertical. And when I'm drawing their Poincare duals, it's something completely different. Like the first direction goes horizontal in the other direction and vertical in the other direction. Everything gets rotated. It doesn't matter. Here's a product of a basic 2 cell with a basic 1 cell. Here's a product of a basic 1 cell with a basic 2 cell. And you might enjoy or not the exercise of seeing that these two directed cell complexes are not even equivalent at all. They're just, as you start filling in the arrows, there's not a directed isomorphism between these two cell complexes. Like this one, you might say, oh, if I put the direction in the other way, it kind of looks the same because the arrow is equal to itself. The pictures, in general, the way you draw these Poincare dually is you draw a picture, like a one cell. A one cell is dual to a codimension 1 interface. A two cell, I can't draw in higher than 2 dimensions very well, so I'm going to draw pictures like this, where I draw kind of the source. So here's the, so this one is the source of this 3 morphism. That's a 2 cell, and then this square is going on here, and then here's the 2 cell and a square in the other direction. And the rule is that beads like to go to the west. They like to, that's sort of a Horace Greeley rule in cell complexes, where you want to pull beads from the northeast to the southwest, or from the southeast to the northwest. So that's what these products look like. Here's a 4-dimensional complex. I really ran out of room on my slide to draw a 4 manifold. So here's 2 3 manifolds. They don't even look like they patch together, but they do. And here's the Poincare dual picture. So here's the sort of 2-dimensional corners of this 4 complex. Here's the 3 cells, and the 4 cell pulls through. And it's completely not invertible. No cell in this is invertible. So that's what tensor products look like. Because you have tensor products, I said this was a closed monoidal structure, so I can talk about the adjoints to this, the Hom tensor junction. So if you figure out what the adjoints are computing, they compute the following. If I have 2 categories, here's a thing I can try to do. I can say if I have 2 categories, I can look at all the functors between them. And then rather than asking for natural transformations, a natural transformation is something that to every object assigns an arrow, and to every arrow assigns a commuting square. I can ask that square to commute up to an arrow. And this tensor product exactly handles those combinatorics of which directions those arrows compute. And so that's what we call them, is we call them fun lax and fun oplex. Fun lax and fun oplex have the same objects. The objects are just functors. In spite of the name, these are just like the categories whose objects are functors from x to y. The lax and oplex tell you what types of morphisms I'm using. And that's sort of a use, that's sort of maybe the main reason originally why this tensor product was studied, was to be able to talk about lax and oplex natural transformations. So, and then the last technical ingredient I'm going to need is, so this is just a list of technical, I'm just making my mise en place. Dan says we don't like French terms, French culinary terms. So the other things I'm going to need, I'm going to need later, like I'm going to need to be able to, this is just me telling you some notation. I'm going to want to be able to localize, like take some infinity category and write down something where I've inverted all the morphisms of some direction. I'll call that construction L, that just forcibly takes anything of dimension higher than n and forces it to be invertible. I'm actually going to want to work with categories with a base point, because my theorem was about a category with a base point. And then instead of taking a tensor product, if you're working with spaces with a base point, the natural product on spaces with a base point is called the smash product. And this is just the lax version of the smash product. You take a tensor product, and then you smash out anything that has a base point in either coordinate. And then the last thing I'm gonna need in my story for you is a directed version of the circle. The circle is one of the most basic important objects in algebraic topology. It's how you take loops, and the usual circle is the space which like looks like the integers, in the sense that it has an integer many winding numbers. The directed circle is just the one where you can only go one direction, so it looks like the natural numbers. And I'll typically write loops of x. Mike once complained that he wanted an arrow on this loops symbol. Maybe we should use that. But anyway, I'm going to write loops of x to mean the loops in x, the directed loops in x, and op-lax natural transformations of those. That's the one that ends up matching the conventions correctly. So okay, now I'm going to go in and tell you, and hopefully I might not even use my whole time. That'll be great. Now I'm going to tell you sort of the actual things that we do in the paper. So this stuff that I told you all before, the literature on infinity categories and lax tensor products is being developed. And we certainly had to write a whole bunch of things down that weren't in the literature yet, but it wasn't, like, I think, really new to us. And this stuff is what we actually sort of did. So, okay, so the first thing I want to do is say the punchline of this slide is something that, of course, you know, which is that the notion of bialgebra is in some sense a square of the notion of algebra. That's like in the name. Bialgebra should be the square of algebra. There's two obvious squares of algebra. One's called bialgebra, and the other is called E2 algebra, and you can ask which one is it. This is the right one. So the way that works is the following. Right, so the reason I was talking about loops was because taking loops of a category adds to its amount of monadality. And if you kind of play, something you might have played with back in the 30 years ago when you were learning about, or 40 years ago when you were first learning about monoidal categories and lax monoidal functors, is you might have noticed that an oplax monoidal functor between monoidal categories feels a lot like a coalgebra. That a coalgebra is an example of an oplax monoidal functor. And you can make that rather precise. One way to say it that just sort of encodes this idea, the way that I'm going to encode it in this language is to talk about the walking monad, the free monoidal category on a monoidal object. So that it's the thing that represents, and then I'll think of it as two categories. It's the thing that represents algebras in the loops category of something. And I can talk about oplax monoidal functors in this language, that they're the oplax pointed functors from something to something. And then the theorem, which I think was first proved in a different context by Hadza Hasanovic, is that if you take the two product, like the walking monad tensored with itself, rather smashed with itself, that's some 4 category. The monad's a 2 category. It's a monoidal 1 category that I've written as a 2 category. So this is some 4 category. And if you force it down to being a 3 category, you get the walking bialgebra. And so Amar proved this in a model of infinity categories that's not known to be equivalent to the model I'm using, in a much more combinatorial algebraic model. It's probably equivalent, but who knows? And then we reproved it in our model. Sort of in the kind of homotopy theorists version of infinity categories. If you don't do this killing down to dimension 3, it's actually really interesting. What you get is like somewhere in the notion of bialgebra. Let's see, I'm going to go back a bunch of slides if I can. Can I go back? Oh, it's going to be slow. So I wanted to really show you the bialgebra axiom again. So this, of course, is the bialgebra axiom. Is if you read a standard paper, this is called the bialgebra axiom. And if you actually look at monad smash monad, you don't get a bialgebra axiom that says that this is isomorphic to this. You get this is some 2-cell, anyway. What you get is a non-trivial arrow between these. And it goes in some direction that I can't remember which way it goes. It goes in some specified direction. And the reason I mention this is just a fun game if you're bored and want to play, is that I'm using sort of one way to say what is a bialgebra is to say that it's a coalgebra in the category of algebras. And another way to say it's an algebra in the category of coalgebras. So you could take the talk I gave you so far, and instead of talking about monad, you could talk about comonad. And take the same thing and look at the smash square of that, and then you'll actually get different directions. So somehow the notion of bialgebra and bicoalgebra start being have a different direction in the bialgebra axiom as you go up. So that's something that I enjoyed figuring out. I mean, I'm sure I'm not the first person, but it amused me when I was doing this. So here's how Amar's theorem works. And I'll just show you, again, I'll sort of show you the incoherent version. So we give a coherent proof that this is of this fact about monad, tensor, monad, but here's sort of when you unpack it, what's going on. And I'm also telling you this so that I can show you some notation. So when you unpack it, what happens is the following. So you take a circle. A circle is something that starts with a base point. I'm just going to write the base point in clear, and then it has a one cell, which is dual to a codimension 1 interface. And you take a tensor product of two circles, so that's crossing. And then I want to work in this smash product. The rule for the smash product is that I smash out any cell that has the base point in either variable. So I'm going to draw in like faint, in gray, the things that get smashed out. And the only cell that doesn't get smashed out is the 2 cell in this product. There's a fact that you know that if you smash two circles together, you get a sphere. You get just a 2 cell from the base point to itself. So the monad is, what is it? When you write down the abstract notion of algebra, you have a single generating object, and then you have some morphisms between products of it. So the basic cell in a monad is the single generating object, and then there's some 2 cells. There's the most interesting one's a multiplication one. There's a unit one that's boring that you can draw, but I didn't have space on the slides. So the 2 cell looks something like 2. You go around twice of the circle. That's this picture, or you go around once, and there's a 2 cell between them. And when you just multiply these together, if you take so when you take the notion of monad and multiply it by itself, you get the interesting things, the first things that don't get smashed out are these crossings, these 3 cells that move you, that pull the 2 cell across the wire. And if you track the directions, what you get is you get a thing that takes a crossing in this order and pulls that multiplication through the wire. So that's a thing that takes 2 of my bullets and becomes 1 bullet. Or I can take a 2-to-1 map and pull it across the wire, but the direction I have takes me from 1 bullet to 2 bullets. And these just become the multiplication and co-multiplication in my Hopf algebra. And then there's some 4 cell that says that if I take the product of 2 of these and pull them through in different directions, you get some 4 cell that fills it in, and then I'm going down to dimension 3 where that 4 cell becomes invertible. So that's basically why you get monad times monad as bialgebra. That's the kind of incoherent version of it. Okay. So I want you to remember that the square of monad is bialgebra. The next thing we had to do was start studying. I should have said, why am I doing all of this? I'm doing all of this because, if I told you I could have given a talk. It would have been over in about 5 minutes, called how to build an algebra. And the 5-minute talk called How to Build an Algebra would be, if I have an adjunction in a category, I can get an algebra out of it. That sum of the data of an adjunction is an algebra in one of the 2 sites. And this is something that's like probably from when adjunctions were first written down, like in a number that probably rounds to 100 by now of years. I don't know how long ago adjunctions and categories were. So that's how you build an algebra. You take an adjunction, you go look out in the world, you find an adjunction, and you get an algebra from it. And I don't want an algebra, I want a bialgebra, I want a Hopf algebra, so I'm going to go find something that looks like a square of an adjunction, and I'm going to just sort of do a squared construction of it. So I just told you the square of monad, the square of algebra is called bialgebra. So now I'm going to start studying the square of adjunction. That's what this is about. So I had to get kind of good at multiplying by adjunctions. So I'm going to write adj for the free adjunction. As I said, it's the thing. If you wanted to do this 5-minute talk where you took an adjunction and got an algebra, that would just be restricting along the inclusion from monad to adjunction. I'm going to write L for the inclusion of the left arrow. That's an epimorphism in the sense that it is a property for an arrow to be adjunctable, to be a left adjoint. And then we had to get good at understanding what happens if I multiply in either variable. And it's something slightly interesting happens. So Claudia and I wrote this theorem down first. The proof in our paper has an error, which is embarrassing to me. And so we had to fix it in this paper. And then Naruki Masuda really kind of cleaned up our proof. We had a slightly long-winded proof that fixed the error, and then Naruki gave a kind of 2-line, like very, very clean proof of this. So what happens is the following. if you multiply, remember, multiplying is kind of has a handedness to it in my world. So if I multiply on one side, then the rule is the following. If I want to ask how, so what am I asking? I'm asking, what is the data if I give you a case cell times an arrow, and I want it to factor through a case cell times an adjunction, meaning that it should be sort of adjunctable in the second variable. What do I have to do when I unpack that? And the answer is, well, I have to factor the boundary through. Well, that's obvious. And then if you compare, the only thing in a k cell times an arrow other than its boundary is a single k plus 1 dimensional thing that fills it in. And all it has to be is it has to be a left adjoint. That's the axiom. On the other side, if I want to factor in the other variable, again, I have to do something with the boundary. And then I look at the filling, and it's not, the condition is not that that filling has to be adjunctable. That turns out not to be the correct condition. Rather, you take the filling, and then you write some other morphism that involves kind of canonical maps between taking adjoints of boundary terms, and you ask that to be adjunctable. So there's an interesting handedness to these notions of like where the left and right order in tensor products gets mixed in with left and right questions about adjunctability. So we did that, and then we used this to do the following. So what we prove is the following. So then what we did was we computed the tensor product of an adjoint with itself. So a square with various adjunctability conditions. And I've given it to you after smashing it out. But roughly what happens is that you get a square, and then you ask various adjunctability. So the various sides of the square each have to be 1 unit of adjunctable. And then there's that filling in the square. And what turns out to happen is that the filling in the square has various adjunctability conditions on it that come from comparing these different adjunctability conditions. And one of the adjunctability conditions is that either that filling or some rotation of it, some mate of it, has to be adjunctable. But another condition is that a different rotation of it has to sort of have 2 units of adjunctability. It has to be like a 2 adjunctable morphism, the same way that you might be used to 2 dualizable objects. And that's what you get when you just multiply edge by edge, is some 4 category with that list of things. But then you collapse it down to a 3 category, and the thing that had 2 units of adjunctability has to become invertible when I collapse down to a 3 category. That's what happens. And now I can give you the first half of our theorem. The first half of our theorem is what I said about kind of taking, I know how to restrict from an adjunction to an algebra, and so I can take the square of that map and write it in dimension 3, and that would take me from, I told you the square of an adjunction in dimension 3 looks like a retract, so plus some adjunctability, and that would restrict to a bialgebra. So that's how we handle, that now handles all of the infinity coherence. So this is, the reason I'm telling you all this is I think it's a good technique. I think it's a good way of handling coherence in high dimensions. At least this is, I think it's good based on one example. So, okay. So the last thing I want to tell you is about the antipode. So this is what should surprise you. I'm like, if every algebra can come from an adjunction. And so you might think every bialgebra is a square of an algebra, every bialgebra should come from a square of an adjunction, and that doesn't happen. What happens is the following, is that I told you that I'm actually getting Hopf algebras. So what is a Hopf algebra? A bad way to define a Hopf algebra is to actually say a Hopf algebra is a bialgebra that emits an antipode. And the reason that's bad is it's a little bit annoying to write down exactly what an antipode should be. A cleaner way to say what is a Hopf algebra is to write down the shear map. So the shear map is something that takes 2 copies of your algebra, duplicates the first variable, and then multiplies in the second variable. So if you're just taking a group, this is the thing that takes g comma h to g comma gh. And if you ask that to be invertible, that kind of 2 to 2 2 and 2 out map to be invertible, that forces the group to be a group and not just a monoid. So the definition of a Hopf algebra is the shear map is invertible. I think I've, again, snuck in some left and right because I told you it was really the opposite. Don't worry. So here's what a picture of the shear map looks like in monad times monad. I take 2 copies of my bialgebra, I co-multiply in the first one, and then I multiply in the second one. And the theorem that we do is we show that this composition becomes invertible in this tensor product. So I think we're going to get snacks early, unless there's lots of questions. So here's the picture proof of that. So this is some 4 category you can compute with. And what we do is and I just I spent a long time drawing this picture, so that's why I'm showing it to you. Here's an unpacking of that shear map in my adjunction times adjunction, and here's some big commutative diagram in some 4 category. This is just in adjunction times adjunction. There's some big commutative diagram, and all of the things labeled either R or L are an adjunctable 3 morphism in a 4 category. And adjunctable 3 morphisms in 4 categories become invertible when you collapse to dimension 3. So that means that, and let's see, these guys just commute for free. They're just like the fact that I can pull a vertex through in some direction versus doing them in the other order. And then there's this 4 cell becomes invertible if I collapse to dimension 3. And so the end result is that this composition becomes this composition that's just invertible. So I went faster than I thought I would, which is great, and I apologize for those who wanted me to go slower. So let me just sort of also say that the same types of technology. Let me just sort of point out one other thing, which is that I didn't actually, in everything I said, had to work in kind of actual bialgebras, and so this is actually true at the level of just tensor products. And the side effect of this is that we can get kind of variations on Hopf algebras, so Hopf monads and so on we can kind of recognize. And so we kind of have now a general machine that says, oh, here's how to build a Hopf monad, and this same proof tells you that it really has an antipode in the sense of Hopf monads. So I think I'm going to actually just stop and see if there's questions that I can elaborate on it. So.